Calculus is all about studying change. So we might be interested in how the height of a projectile is changing over time. We might be interested in how the volume of a balloon changes as the radius changes, or vice versa. We might be interested in how the radius of a balloon changes as you increase the volume. We might be interested in how the demand for a product changes as you change the price. So that's what calculus is all about, and you probably learned all of that in Calculus 1, right? So um, you probably remember this formula too. The formula for the definition of a derivative, if we have some function, f of x, where the whatever f represents, maybe it represents volume, and maybe x is the radius. But we've got some relationship. We've got a quantity f of x that depends on x. So x is considered the dependent variable. And the derivative is defined to be the limit as h goes to 0 of the difference in the value of the function over h. And h is just an incremental change in x, right? So we're looking at the value of the function at x plus h minus f of x. So we're looking how it changed. If you add a little bit of h to the x, how does that change the value of the function over the small change in x? Okay, and then we're taking the limit as that little bit change goes to 0. And that's the definition of a derivative. Now, we could also think of that as, essentially the change, if we let y equals f of x, we can think of that the numerator, this numerator in the definition up here, this is effectively the change in y, right? And this h is effectively the change in x. So we can rewrite this definition of derivative as being the limit as the change in x goes to 0 of the change in y over the change in x. And one of the notations that we use in calculus is this dy dx. So dy represents an infinitesimal change in y over an infinitesimal change in x. Okay, so it incorporates that limit as delta x goes to 0. So so we can see that the derivative can be used to find the instantaneous rate of change for a function, and with respect to a dependent variable x. And in graphical form, that instantaneous rate of change represents the slope of the tangent line at that point. Okay, so this first example, if you haven't already looked at it and tried to answer these questions on your own, you should pause the video here and you can answer these questions on your own, just intuitively. Even if you had not had calculus, you should be able to answer these questions. Well, maybe some of the notation is a little, might be, if you hadn't had calculus, it might be a little weird. But try it on your own and then come back and we can go through it together. All right, so in this example 1, we're told that at 10 a.m. on June 23rd of 2020, the temperature in St. Paul, Minnesota was 72 degrees and rising at a rate of 2 degrees Fahrenheit per hour. Okay, so the first thing we're asked is just to estimate the temperature in St. Paul at 10:30. Okay, so it was 72 degrees at 10 and rising at a rate of 2 degrees per hour. So what do we need to do to figure out what we're estimate the temperature at 10:30? So 10:30 is just a half hour later, right? So, and if it's rising at 2 degrees per hour, then in a half hour it would rise one degree, right? So we can basically take this 72 degrees Fahrenheit and we can add 2 degrees Fahrenheit per hour times the number of hours. In this case, it's just half an hour. So we get half an hour. And what we'll end up is 73 degrees Fahrenheit. So now this part B asks if f of t represents the actual temperature in St. Paul in degrees Fahrenheit, where T is in hours, since 10 a.m. on June 23rd. Interpret the following statements, including units. So f of 2, okay? So f of 2. So in this case, the input to the function is t, and in this case, t equals 2. But t is the number of hours since 10 a.m., right? So t equals 2 would be 2 hours after 10 a.m. So essentially, this represents the temperature at noon, right? 12 p.m., right? 2 hours later, 2 hours after 10 a.m. And it's telling us that the temperature at noon is 75 degrees Fahrenheit. Okay. So f is the actual function. It's not some sort of linearized function. It's just an actual function. And then we have f prime of 2. So f prime is the derivative at 2. So this is telling us the rate of change of whatever f represents, and in this case it's for representing temperature. So it's the rate of change of temperature with respect to time. Okay, so this is saying that at t equals 2, which again is 12 noon, so I'm just going to write this at 12 p.m., the temperature is increasing, right? Because this is our change. This is our change in temperature with respect to time, and it's positive, so it's increasing. So it's increasing at a rate of 0.5 degrees Fahrenheit per hour, right? Because the derivative of the function is the rate of change of the function with respect to the dependent variable, in this case time. Okay, so that means the units of f prime are going to be in degrees per hour, degrees Fahrenheit per hour. All right, so the next question is asking us to find a formula for a linear approximation of the temperature based on the information given at 10 a.m. Okay, so we just want to turn what we did in part A into a function. So we're trying to find a function for t, right? We're going to approximate the function for t. So I'm going to say it's approximately equal to 72 degrees, right? 72 degrees Fahrenheit, plus, and it's rising at 2 degrees per hour. So if we take 2 times the time, then we'll get the temperature at that time. So our result will be in degrees Fahrenheit. And t, so I can write where t is the number of hours since 10 a.m. is the number of hours since 10 a.m. All right. Let's see. The next question says, would this linear approximation be a reasonable estimate of the temperature in St. Paul at 11 a.m.? And explain your reasoning. So, this is kind of an open-ended question. It kind of depends on what's going on with the weather pattern. But I would say, if we don't know anything else about what's going on with the weather in St. Paul, then it's probably a pretty decent approximation for at 11 a.m., right? Because at the 11 a.m. isn't too far removed from 10 a.m., right? It's only an hour. And so we're it's probably reasonable. So, and I would say the reason would just be because 11 a.m. is t equals 1. Oops, okay, is t equals 1, which is fairly close to 10 a.m. So that's probably what I would write. Fairly close to 10 a.m. And you could also, reason that okay, at 10 a.m. The temperature is probably still going up, um, and maybe at 2 degrees per hour. I don't know, but it's probably still going. It's going in the right direction, right? Now, the next question asks, would this linear approximation be reasonable to estimate the temperature at 7 p.m.? And no, that would probably would not make sense. Now, again, I don't know what's going on with the weather, but 7 p.m. is t equals 9, right? So that's 9 hours later, and the normal variation in temperature, it goes up, right, and it kind of plateaus, and then it starts coming back down in the early evening, right? So by 7 p.m. the temperature is probably coming back down. So it wouldn't make sense to use this linear model, because it would tell you that, if 72 degrees plus 2 times 9 hours would put you at 90 degrees. Now, it's probably not. That's probably not what's happening at 7 p.m. The temperature is probably not going up. So we don't know that, but I would say in general, this would not be a good model. This linear approximation would not be a good model for 9 hours later on a given day. So if I was going to write this out, I'd probably say that 7 p.m. is t equals 9, right? And it is not likely that the temperature is still uh, is still increasing at 2 degrees Fahrenheit per hour at that point. So that takes care of the first example, and I'll meet you in the next video.